Now let's just take a look at this one demo to give you a tactile feeling of what I'm talking about. Please play it.
Traditional LLMs capture foundational knowledge, while reasoning models help solve complex problems with thinking tokens. Here, a prompt asks to seat people around a wedding table while adhering to constraints like traditions, photogenic angles, and feuding family members. Traditional LLM answers quickly with under 500 tokens. It makes mistakes in seating the guests, while the reasoning model thinks with over 8,000 tokens to come up with the correct answer. It takes a pastor to keep the peace.
Okay. As all of you know, if you have a wedding party of 300 and you're trying to find the optimal seating for everyone, that's a problem that only AI can solve or a mother-in-law can solve. And so that's one of those problems that co-op cannot solve. Okay, so what you see here is that we gave it a problem that requires reasoning, and you saw R1 goes off and it reasons about it, tries all these different scenarios, and it comes back and it tests its own answer. It asks itself whether it did it right. Meanwhile, the last generation language model does a one-shot. So the one-shot is 439 tokens. It was fast, it was effective, but it was wrong. So it was 439 wasted tokens. On the other hand, in order for you to reason about this problem, and this is just that was actually a very simple problem. You just give it a few more difficult variables, and it becomes very difficult to reason through. And it took 8,000, almost 9,000 tokens. And it took a lot more computation because the model's more complex. Okay, so that's one dimension. Before I show you some results, let me explain something else. So the answer, if you look at Blackwell, you look at the Blackwell system, and it's now the scaled up NVLink 72. The first thing that we have to do is we have to take this model, and this model is not small. It's, in the case of R1, people think R1 is small, but it's 680 billion parameters. Next generation models could be trillions of parameters. And the way that you solve that problem is you take these trillions and trillions of parameters and this model, and you distribute the workload across the whole system of GPUs. You can use tensor parallel. You can take one layer of the model and run it across multiple GPUs. You could take a slice of the pipeline and call that pipeline parallel and put that on multiple GPUs. You could take different experts and put it across different GPUs. We'll call it expert parallel. The combination of pipeline parallelism and tensor parallelism and expert parallelism, the number of combinations is insane. And depending on the model, depending on the workload, depending on the circumstance, how you configure that computer has to change so that you can get the maximum throughput out of it. You also sometimes optimize for very low latency. Sometimes you try to optimize for throughput. And so you have to do some in-flight batching. A lot of different techniques for batching and aggregating work. And so the software, the operating system for these AI factories is insanely complicated. Well, one of the observations, and this is a really terrific thing about having a homogeneous architecture like NVLink 72, is that every single GPU could do all the things that I just described. And we observe that these reasoning models are doing a couple of phases of computing. One of the phases of computing is thinking. When you're thinking, you're not producing a lot of tokens. You're producing tokens that you're maybe consuming yourself. You're thinking. Maybe you're reading. You're digesting information. That information could be a PDF. That information could be a website. You could literally be watching a video, ingesting all of that at super linear rates. And you take all of that information and you then formulate the answer, formulate a plan to answer. And so that digestion of information, context processing, is very flops intensive. On the other hand, during the next phase is called decode. So the first part we call prefill. The next phase of decode, requires floating point operations, but it requires an enormous amount of bandwidth. And it's fairly easy to calculate. You know, if you have a model and it's a few trillion parameters, well, it takes a few terabytes per second. Notice I was mentioning 576 terabytes per second. It takes terabytes per second to just pull the model in from HBM memory and to generate literally one token. And the reason it generates one token is because remember that these large language models are predicting the next token. That's why they say the next token. It's not predicting every single token, it's predicting the next token. Now we have all kinds of new techniques, speculative decoding and all kinds of new techniques for doing that faster, but in the final analysis, you're predicting the next token, okay? And so you ingest, pull in the entire model and the context, we call it a KV cache, and then we produce one token. And then we take that one token, we put it back into our brain, we produce the next token. Every single time we do that, we take trillions of parameters in, we produce one token. Trillions of parameters in, produce another token. Trillions of parameters in, produce another token. And notice that demo, we produced 8,600 tokens. So trillions of bytes of information have been taken into our GPUs and produced one token at a time, which is fundamentally the reason why you want NVLink. NVLink gives us the ability to take all of those GPUs and turn them into one massive GPU, the ultimate scale up. And the second thing is that now that everything is on NVLink, I can disaggregate the prefill from the decode, and I could decide I want to use more GPUs for prefill, less for decode, because I'm thinking a lot. It's agentic. I'm reading a lot of information. I'm doing deep research. Notice during deep research, you know, and earlier I was listening to Michael, and Michael was talking about him doing research, and I do the same thing. And we go off and we write these really long research projects for our AI, and I love doing that because, you know, I already paid for it. And I just love making our GPUs work. And nothing gives me more joy. So I write up, and then it goes off and it does all this research, and it went off to like 94 different websites, and it read all this, and I'm reading all this information, and it formulates an answer and writes the report. It's incredible, okay? During that entire time, prefill is super busy, and it's not really generating that many tokens. On the other hand, when you're chatting with the chatbot, and millions of us are doing the same thing, it is very token generation heavy. It's very decode heavy, okay? And so depending on the workload, we might decide to put more GPUs into decode, depending on the workload, put more GPUs into prefill. Well, this dynamic operation is really complicated. So I've just now described pipeline parallel, tensor parallel, expert parallel, in-flight batching, disaggregated inferencing, workload management, and then I've got to take this thing called a KV cache, I've got to route it to the right GPU, I've got to manage it through all the memory hierarchies. That piece of software is insanely complicated.